Okay, welcome to today's class again. We are going to continue from where we stopped in the previous video. However, today we will be looking at Boolean Algebra. We will look at Boolean Algebra and how is Boolean Algebra used in computer programming. In what case? How does it relate to computer science? Why are we studying Boolean algebra in computer science? These are the things we'll talk about. We have some premise on which the Boolean algebra works. We're going to start with those ones, basic concepts in Boolean algebra. And they are, we list them out. A plus 0 is equal to A, that is A or 0. If we are going to do a truth table on this side, we have A, 0, so we have 0, 0, 1, 0. A plus 0, and it's A or 0. So this is going to give you 0, and this is going to give you 1. Which means whatever A is what A plus 0 is. That is a proof of that. The next we have is A plus 1 is equal to, let's do A plus 1. A plus 1, A, 1, A or 1. This is going to give us 0, 1, 1, 0. This will give us 1, 1 because it's an OR operator. So we have 1. Then the next we have is A plus A. A plus A will be equal to A. The reason is simple truth table proof. You have A and you have A. You have 0, 0, 1, 1. So A plus A will be 0, 1. A plus A will give us A. That is that. The next we have is A plus A bar, which is negation of A, which is the opposite of A, and that will give us 1. Now, why is that so? If we go over to the truth table, we are proving it from the truth table. If we have A there, negate A, that's negation of A. You have 0, 1. The negation is 1. The negation of this is 0. And so A plus A bar will now give us 1, 1. Whichever one, because it's the A or operator. Then the next we have is A dot 0. A dot 0 will give us 0. A and 0, because this is AND operator. So we saw what we did in the last video where we used a circuit diagram to explain it. So A and 0 will give us 0. If we use a truth table, we have 0, we have A dot 0, we have 0, 0, 1, 0. 0 and 0 will give us 0, 1 and 0 will still give us 0. So A dot 0 will give us 0. Now let's do A dot 1. A dot 1. A dot 1 will give us A. How do we get that? We use our truth table again. The mathematicians will do some other proof. If we do our truth table, we have A and we have 1, I have 0, 1, 1, 1. So we have A and 1. 0 and 1 will give us 0, 1 and 1 will give us 1. True and true. So you see that this is a reflection of A. 0, 1, 0, 1. So A dot 1 will give us A. Now the next we'll use as a premise is A dot A bar, which is the negation of A. That will give us a 0, because the negation of A will be the negation of A will be 1 and 0, and so A dot A bar negation will give us 0, 0. This is that is that. So another one we have is A dot dot A bar bar, which is negation of the negation, is equal to A. We could still use a truth table to demonstrate that. We have A. If we do this, this is A, this is the negation of A, and so the negation of the negation will give you the negation of this 0, the negation of this will give you 1. So we discover that A and A bar bar will give you the same thing as A. Another thing we will work with again is A dot A. Remember, when we say dot in this case, we are talking of and. So A and A will give us A. Will give us A. So if we do that, use our truth table again, we have A, 0, 0, 1, 0, 1. So A and A will give us 0, 1. So it's a repetition of A. So we bear that in mind. Now, these are some of the basic postulates that we are going to use to do our Boolean algebra. At this point, we'll come to some laws in Boolean algebra. The first of it is the commutative law. The commutative law. In the commutative law, what does the commutative law say? The commutative law says that A dot B is the same thing as B dot A. Again, A plus or B is the same thing as B plus A. That is a commutative law. Commutative law. Now, how does this apply to programming, to computer programming? We are going to prove this law, but how does it apply to computer programming? What this means, we will show you using a truth table to first of all prove it. If you have A and B, we'll do 0, 0, 0, 1, 1, 0, 1, 1. So A dot B will give us A and B, so you have 0, 0, 0, and 1. Now, if we do B dot A, you are going to have 0, 0, 0, and 1. The truth table shows that A dot B is the same thing as B dot A. we have used the truth table to show the cumulative law. Now let's try the truth table with the OR operator, to prove the cumulative law. Although the mathematicians will use other ways to prove it, but we are using the truth table for now. So if we have A and B, we convert this to A or B. We do A or B, and we also have B or A. Now, if you do A or B, you have 0 there, 0 and 1, we have 1 there, 1 and 0, we have 1 there, 1 and 1, we have 1 there. Remember, 1 is truth, 0 represents false. So if we go over to B or A, the same result appears. This goes on to prove that A or B is the same thing as B or A. This is the cumulative law in Boolean algebra. Now, how does this really apply in computer programming? How do we use it? Let's assume that we have a case where the Bayelsa state government wants to give scholarship to first class students. So A is now first class students, A is first class students, and then B is now computer science students. Now, how does this cumulative law apply? Let's assume that the Bayelsa state government wants to give scholarship to first class students and who are also in computer science. First class students and computer science. Now, if we go from this route, A, meaning that for you to choose to select those students who meet this criteria, you can first of all come to look at all the first class students in NDU, which is now A, and then you now look at all the first class, no, that is it. We use this to demonstrate this. All the first class students in NDU and in computer science. This is an and. They are first class students and they are in computer science. Now we are saying that it is the same thing as saying pick the computer science students and then pick the first class out of them. We are saying the same thing. If you go from this other route, picking the first class in the university, before picking the computer science students, is the same thing as picking the computer science students and then picking the ones who have first class. So in computer programming, what you now do is, which route gives you a smaller search space for you to be able to get your work done. And understanding of this will enable you pick which one has a smaller space, because you now know that A.B is the same thing as B.A. Now, come to think of it, if you pick all the students in first class, look at the work done, all the computer science students, all the first class students in the university, and then pick the computer science students from them, the work you are going to do. Then in this other case, you pick the computer science, you come to the computer science department and pick the first class students. So the conditions that will be given to you based on your understanding of Boolean algebra will enable you know which of the search space will do better for you and make the work easier for you. So that shows that B.A.B is the same thing as B.A. So when you are writing your computer program, you are now going to put that into consideration. Now let us look at the case of A or B, or B of A, B or A. It's the same thing applies. In some cases, your programming, you have to move from left to right or from right to left, whichever one works better for you. That is the reason for using this Boolean algebra. Now the next thing we are going to look at is the distributive law. The distributive law. So we are going to look at the cumulative. We have looked at the cumulative law. Now we are going to look at the distributive law. Remember, the plus operator is the same thing as the or operator. And the dot there is an and operator, as we did in the previous video. For the purpose of showing you, we wouldn't want to be writing all these things, so we are using the mathematical notations. So plus is or, dot is and. Now the next we want to look at is the distributive law. The distributive law, what does the distributive law say? Distributive law. The distributive law says that A dot B plus C is the same thing as A dot B plus A dot C. That is the distributive law. A and B. When you say A or B or C and A, or in other words, A and B or C, now mind you, in this case, the OR operator works first, and then the AND operator. It's the same thing as saying that A and B or A and C. So let us use truth table to verify if this is true. To verify that, we use our truth table again. We use our truth table again, and we have A, B, and C. 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and then the last one, I'm going to write it somewhere here. A, B, C. The last one will be 1, 1, 1. So if we do A, here we are doing the bracket first. So we have B plus C, which is B or C. We have 0 and 0, that, we have 1 there, we have 1 there, we have 1 there, we have 0 there, we have 1 there, we have 1 there. Then in this case, the 3, so we have B plus C, we have 1. This is B plus C. Now if we do A dot B plus C, we now look at A and B or C. Here we have gotten B plus C, which is B or C, then A and it, so we have 0 and 0, we have 0 there, we have 0 there, we have 0 there, we have 0 there, we have 0 there. Here we have 1. because you're going to have 1 and 1. And 1 and 1, we have 1. And then here, we have A dot B plus C. Here we also have 1. So this is the left-hand side. So we want to do the right-hand side to see if we are going to get the same thing with the left-hand side. So A and B, sorry, A plus and B, then we are going to do A and C, and then we are going to do A dot B plus A dot C. So A and B, 0 and 0, we have 0. A and B, 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 we have 1. And A and B on this side will also have 1. We're going to wipe that point to create room for that. So we have A and B. So A and B, that's 1, 1. Sorry. We'll place those ones here. A, B. A and B. So A here, no, we're going to include the C as well. C. So we have 1, 1, 1. So A and B, we have 1, A dot B, we have 1 here. Now we go to the next one, A and C. A and C, 0, 0, we have 0 there. 0, 0. A and C, so we have 0 there. A and C, 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 we have 1 there. A and C, we have 0 there. A and C, we have 1 there. Now the next is A dot B or A dot C. If you look at this, we have 0 there, we have 0 there, 0 there, 0 there, 0 there, 1 here. Because it's an or, we also have 1 here. And A dot B plus A dot C, here we'll also have 1. Now, when we look at this truth table, we will see that A dot B plus C is the same thing as this. We go to the next line, it's the same thing, 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 and we also have the same thing. So that proves the distributive law that A dot B plus C is the same thing as A dot B plus A dot C. Now, how does this affect us as computer programmers? How does this affect us as computer programmers? When we have two conditions, A or B, and C, is the same thing as saying that A and B or A and C. Let's take an example. The person is either a student or let's say the person is either in computer science or in biology. Let's say biology, computer science. Now, let's take this as the first class student. The first class student, we want students who are in computer science or biology, and then first class students. It's the same thing as saying that going to computer science, pick the first class student, or biology, and also taking the first class student. Something like that. Well, when we will start programming, we will see how we are going to use this. But you could express your conditions using these things, simplify the Boolean algebra, and use it to write your code. Now, the next thing we are going to look at, we have verified the commutative law and the distributive law. We have verified the commutative law and the distributive law. Now, we'll wipe this. Now, in the distributive law, there's something here that says A or B dot A dot C is the same thing as A plus B dot C. Now, if we have three conditions like this, we say A or B and A or C, we are able to understand that this is the same thing as A or B and C. Now, let's look at a proof to that. We'll prove it mathematically this time, but we can still use the truth table. We agree that if we, going by the distributive law, A and A will give us A dot A plus A dot C plus B dot A plus B dot C. That's this dot this will give you this, this and this will give you this, this and this will give you this, this and this will give you this. Now, if you look at that, you will see that these three have a common factor. A common factor, A. If we bring out the common factor, that is dot, you will see that we have A plus C plus B plus B dot C. And A dot A and A, this is where A dot A is A, so we can just say 1. We can just say 1. So we now have 1 here from our assumptions and our first set of these things that we proved there. So, and OR operator, because we now have a 1 here, which is OR, it means that this expression will give us 1, which is A dot 1, which is A. So we now have plus B dot C. So A dot 1, which is A dot this, will give us A. From our assumptions or from our findings in the first set of this is proved. So we have A plus B dot C. So this shows that this is equal to this. Now, why is it important to me? If I have three conditions, A, B, and C, and I have A or B and A or C. If I have three conditions of that sort, and I want to program, instead of me writing the code to express this, let us now use the truth table, although we have proved it mathematically here, that A or B and A or C is the same thing as A or B and C. That's what we have done here. We can prove this using our truth table. We can prove this using our truth table, although we have proved it mathematically here. We can say A or B, A or B, A or B. We can also have A or C. Then we now have A or B and A or C. Now we have 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 0, 1, 1, 1, 0, 1, 1, 1. So if we do that, now A or B, we have 0, 0, 1, A or B, 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 A or B. That's that. Now A or C, for the A or C, we have 0, we have 1, we have 0, we have 1. A or C, we have 1, we have 1, we have 1, and we have 1. That's A or C. So A or B and A or C, A or B and A or C. So now we are using AND here. So we have 0, 0, 0, 1, 1, 1, 1, 1. That is the left-hand side. Now B and C, we want to do B and C, B and C. So when we do B and C, we have B and C, so we have 0, B and C, we have 0, we have 0, B and C, we have 1, B and C, we have 0, we have 0, we have 0, and we have 1. That is B and C. Now A or B and C, A or B and C, A or B and C. Now A or B and C, A of this we have 0, we have 0. Sorry, that's A or B and C, or so we have 0, we have 1, we have 1, 1, 1, 1. Now, if we look at this truth table, we see that these two columns are the same. These two columns are the same. Meaning that this expression, which is on this one, is the same thing as this expression. So if I'm programming, these are programming, if I have three conditions, where I say condition A or condition B and condition A or condition C, instead of me to write this code to be doing all this, I will write the Boolean expression and simplify the Boolean expression and get this. When I get this, you find that coding this is simpler and easier than coding this other one. So that is one of the reasons for our Boolean expression. So we have gotten the commutative law, the distributive law, and so the associative law. Let us look at the associative law. We have looked at distributive law, and looked at commutative law. So the next law we are going to look at is the distributive law. Commutative law, the distributive law, and so we have the associative law. What is the associative law? It's A dot B dot C is the same thing as A dot B dot C. Second one says A dot B plus C is the same thing as A plus B plus C. This is the associative law. So if you do A and B before you AND it with C, is the same thing as B and C before you find the AND with A. So what that means is that if we perform the AND operation between A and B first, and performing the AND operation of that result with C is the same thing as performing the AND operation between B and C before performing the AND operation with A. If you go on to the OR operator, A or B getting that result before performing the OR operation with C is the same thing as performing that of B and C before A or that result. We are going to use our truth table again to demonstrate these two things, this law. So A dot B A dot B dot C now A and B are going to have A and B, so we have 0 there, 0 there, 0 there, 0 there. Remember, this is AND, 0 there, 0 there, 1 and 1. Now, these results and C, so we have this and this, we have 0 there, 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 and 1. This is the left-hand side of this equation. Now let's go over to the right-hand side. B dot C B dot C, B and C. So we have 0 there, 0 there, 0 there, 1 there, 0 there, 0 there, 0 there, and 1 there. Now, if you now have to do A and B, we have gotten B dot C. That is on this side. Now we want to do A and this. So A and this, A dot B dot C. So we are adding A and this column, BC, B dot C. So this and this, we get 0 there, we get 0 there, get 0 there, we get 0 there, we get 0 there, we get 0 there, we get 0 there, and we get 1 there. So when we look at this is the left-hand side of this equation, expression, and this is the right-hand side. So are they equal? Are they the same? You see that? You see that they are the same everywhere. So this goes to show us in the truth table that A dot B dot C is the same thing as A and B and C. That goes to show our associative law. So, if you have three conditions, you might choose to, when you are programming, you might choose to AND this before and find the AND of this before coding this, or you might choose to code B and C first before you code it with A. So it's the same thing. That's what that tells us. So let's go to the OR operator and see if the associative law holds with the OR operator. Okay, let's see, use the OR operator in this case now. So I have A or B, and then A or B or C. We do that. A or B will give us 0 there, 0 there, 1 there, 1 there, 1, 1, 1, and 1. Then A, the outcome of this, which is this, or C, we now have these two, we have 0 there, 1 there, 1 there, 1 there, 1 there, 1, 1, 1. So we have gotten the left-hand side of the expression. Now the right-hand side of the expression, we have B or C, and then we have A or B or C. Now B or C will be B or C, we have 0 there, we have B or C, we have 0 there, we have 1 there, we have 1 there, we have 1, we have 0 there, we have 1 there, we have 1 there, and we have 1. Now A or B of C, now we are going to OR A and this. So this and this, we get 0 there. We have 1 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 there. And we have 1 there. Now, this is the right-hand side of the expression. Now, when we compare these two columns, you see they are the same. They are the same. Proving that A or B or C is the same thing as performing the operation B or C before we now have A or B. That proves our associative law. Showing A or B or C is the same thing as B or C first before we are oiling it with A. So that is the associative law. So we have gotten some laws in Boolean algebra, and so we are going to move on to the next of it. The application of these laws will really come into play when we will start writing our codes. However, it is proper for us to understand these things now. We say A and B or A and C. A or C and B. So if you have A and B or C, is the same thing as A and B or A and C. Now, the other one says if you have A or B and A or C, meaning you have 3 conditions here, it's the same thing as B and C or A. These things will really come into play when we will start coding with our conditions. Now, the next thing we are going to look at again now at this point is what is called the Morgan's theory, the Morgan's law. The Morgan's law, called the Morgan's first law. So what does the Morgan's first law say? The Morgan's first law says that A dot B bar, in this case bar means a negation, the opposite of the operation. That's what we mean. So if we say A is 1, then A bar is 0. If A is 0, then A bar is 1. The negation of it. That's what it means. So the Morgan's first law says that A dot B bar, that is A and B, you add it and you get the negation of it, is the same thing as A bar plus or B bar. The mathematicians will prove it, however, we will use our truth table to confirm if this really works. And we will use it in our programming in future. So, if we want to use our truth table, we now have A, B, A bar, B bar, A dot B, A dot B bar. Now, if you look at A, 0, 0, 0, 1, 1, 0, 1, 1. Now, A bar will be 1, 1, 0, 0. B bar will be 1, 0, 1, 0. A dot B, A and B will be 0. A and B will be 0. A and B will be 0. A and B was 1. Now A and B bar, which is the negation of A dot B, will now be 1, 1, 1, 0. That is A dot B bar. That is the left-hand side of the equation. Now let us try the right-hand side of the equation. If we, for the sake of our A bar, will be 1. Okay, we have A bar here, B bar already. So if we come over here and do A bar plus B bar, A bar or B bar, so here we have A bar or B bar. So this or this, we have 1. A bar or B bar, we have 1. A bar or B bar, we have 1. A bar or B bar, we have 0. Now this is the right-hand side of the equation, while this is the left-hand side of the equation. If we look at this, we compare them, we discover that the two columns are the same. The two columns are the same. That goes to show that A dot B bar is equal to A bar plus B bar. Remember, bar means negation. A bar, B bar means negation. The negative or the opposite of A. The opposite of A. All right, the opposite of A. This is opposite of B. And then A dot B bar is we perform the AND operation and then the opposite of the AND operation. Here we have the negation of A, the opposite of A, or the opposite of B. And we discovered using our truth table that A dot B bar is the same thing as A bar or B bar. These things will help us. So if we now have a condition A and a condition B, you are given those, and you want the negation of it, all you need to do is you get A negation or B negation, and you don't need to stress yourself over this. When you write your code, you see how this works. Okay, that is De Morgan's first law, which we have proved with our truth table. We're going to go to De Morgan's second law. De Morgan's second law says that A plus B bar, that is to perform the OR operation and take the negation of it, is the same thing as A dot B, A bar dot B bar. A very simple way to understand this is to look at this. On this side you have AND, this side you have OR. On this side you have OR, on this side you have AND. So we're going to prove this using our truth table again to see if this actually works. You have A, B, A bar, B bar, A or B bar. So now we have A, B, A bar, and B bar. So we want to do A or B. A plus B, then A plus B bar. So this will give us the left-hand side of the equation. So A or B will be A or B. A or B will give us 0 there, 1 there, 1 there, and 1 there. The negation of it, which is the negation of this, will give us, the negation of this row will give us 1, 0, 0, 0. That is the left-hand side of the equation. Now A bar and B bar, that is this and this. So we do that here. A bar dot B bar. So we have A bar and B bar. So we have 1 there. Here we have, and so we have 0 there. And so we have 0 there. And so we have 0 there. Now this is the right hand side, while this is the left hand side. So this is our left hand, and this is our right hand. So when we compare the two, we discover that the two columns are the same. That goes to show, to prove that A or B bar, the negation of A plus B, is the same thing as the negation of A and the negation of B. That is the Morgan's second law. Now these things can be, in computer science, we can use them in programming, in our circuits, and and all the rest. We can use them in programming, our circuits, and all the rest. We can demonstrate this with expressions. If you have expression, you say expression A is this, expression B is this, expression C is this. When you list out your expressions, you can now write the expressions, and where it is possible, you simplify them. And when you simplify them using these laws and these theories we have put forward, you simplify them, that makes your coding easier. When we get to loops, we are going to see how we are going to use these things in our control constructs. So you have seen how we have used some of these laws. We have seen how these laws work. We have talked about the primary laws, the primary things in Boolean algebra. We have talked about I'll list some of them out here. We have used the OR operator, the AND operator, to see how we have used them to prove these laws. So some of the things we have done, we have used the AND operator in the previous video. We have used the NOT operator, which is the negation, that's the NOT operator. We have used the OR operator, and we have used our parentheses where we use our brackets. Now we have also come up with some laws, some fundamentals, which are A or 0 gives us A or 1 gives us 1, A, or A gives us A, and 0 gives us 0. We saw how we use A and 1 to give us A dot A bar, negation, A dot A bar gives us 0, A double negation gives us A dot A gives us A, and then we saw the cumulative law where we say A dot B is the same thing as B dot A. We also said A or B is the same thing as B or A. The same thing applies. We also looked at, that is the cumulative law. Cumulative law. We also have A dot B, okay, that's the cumulative law. Then we have the distributive law. A dot B plus C is the same thing as A dot B plus A dot C. This is the distributive law. The distributive law of this operation over the other operation. We also said A plus B dot A plus C, we saw that as equal to A plus B dot C. That is the distributive law as well. Then we went on to look at the associative law, where we say A dot B dot C is the same thing as A dot B dot C. A or B dot C is the same thing as A plus B dot C. This is also the associative law. Associative. Let's write it this way. Associative law. We also went further to talk about the Morgan's law, the Morgan's theory. In the Morgan's theory, we proved that A dot B negation is the same thing as the negation of A or the negation of B. That's the Morgan's first law. The Morgan's second law, we now have A or B negation is the same thing as A negation dot B negation. So these are the laws we have proved and we have showed. And all these laws we will be using to make programming easy for ourselves. These laws we will use to make programming easy for ourselves. In the next video, we will emphasize and come up with examples and examples of how these laws are applied in our programming and see how we can use the simplification of these Boolean algebra to make programming easier and faster. When the algebra is it's simpler, it's easier. When we simplify it, it reduces the search space and makes your program run better and more efficient. In subsequent video, we'll talk about that. At this point, we'll come to the end of today's video. Thank you very much.